Next, I want to look at closed system exergy balances, and then we also want to look at systems with flow and exergy calculations for those. So between the beginning and end of a process, the properties will change, which means that the exergy will change. Okay? Part of it's due to whatever's happening work or heat transfer wise in the system, and part of it is due to those irreversibilities that are always going to occur. So if I do a balance on this, for a closed system, the difference between the final and initial state of the exergies will be the amount of heat transfer that happened times 1 minus T naught divided by T of the boundary. It's usually notated a T sub J or T, some sort of T indicating that I might have various places where heat transfer is happening at different temperatures. But this is the temperature that the heat transfer is actually happening at the boundary. T naught, of course, is the dead state temperature. And of course, the amount of heat transfer happening. The work and the potential for work, if it had all happened at the dead state pressure, okay, is also going to be part of that change. And then T naught times the entropy generated. So I've got the exergy transfer due to heat transfer, the exergy transfer due to work, and then exergy destruction. So this is that entropy generation. So it's a way of quantifying this entropy generated, but in terms of an energy quantity. So that last term there is frequently just called exergy destruction, and it will always be positive or zero. Okay? If entropy generated is positive, and T, of course, has to be temperature or thermodynamic temperature, so therefore it's positive, then if this is positive, this must be positive. The only way it can be zero is if there are no irreversibilities. So that means you're talking about an imagined system, one of our reversible cases that we imagine to get calculations going, but not for a real state. You can never get negative exergy destruction. But now this exergy change, E2 minus E1, that it can be positive, negative, or it could be zero. So exergy change across a process may be positive, negative, or zero, but exergy for a state, always positive. Exergy destruction, always positive or zero. If we do this for a system that has flow, I end up with an incredibly similar statement, except for that I'm going to have to deal with exergy of a flowing stream. Now remember, part of the energy required to move things becomes sort of a PV quantity, and so I end up with H's rather than U in a flowing stream as my energy. And so I have, instead of a change in U, I have a change in H. Then, of course, the same change in the reversible work at T naught, and then my kinetic energy and my potential energy. Most times, we only have one stream in and out, so I can look at it a little bit simpler in this form. And so I can see that if I wanted to solve for exergy destruction, the rate of exergy destruction is equal to these terms here. Now, when I look at this, if I look at the exergy change from the inlet to the outlet of a process, all of those enthalpies and entropies of the dead state will subtract away. So in practice, I really don't need to know the properties at the dead state. I only need the temperature and pressure, because temperature will show up here. Actually, I guess I really don't even need the pressure for this particular formula. So I can calculate exergy change for a flowing process with one stream in and out. and I can use this to calculate exergy destruction. So here we have refrigerant 134A coming in at negative 10 degrees C as a saturated vapor. We're going to put this into a well-insulated steady-state compressor at a rate of 0.5 kilograms per second. The refrigerant exits the compressor. The pressure is 5 bar. Kinetic and potential energy changes we can ignore. And the rate of exergy destruction at 25 degrees C, 1 bar. If the compressor is reversible, what will that be? Now, I've already said here that I'm assuming it's reversible. I'm assuming it's well insulated. What did I say were the factors that are going to cause exergy to be destroyed? I said it's going to be friction, it's going to be heat transfer. Other things like explosions and things like that also are irreversible, but really our big two are heat transfer and friction. So I'm assuming that the friction is negligible by saying it's reversible, and I have no heat transfer since it is well insulated. So I expect this should be essentially no exergy change. So let's see what happens if we do these calculations. So I have the data at the inlet and the exit. When I throw this into the formula, I have my enthalpy at the inlet minus the exit, my entropy at the inlet minus the exit, okay, minus my work. My work happens to be the enthalpy at the inlet minus the exit. So these are in fact going to cancel. I'm left with T naught delta S. And if it's well insulated or adiabatic, and if it is reversible, then delta S is 0, and I get 0 as my answer. One last topic that I want to cover very briefly is second law efficiency. It's also called an exergetic efficiency. A second law efficiency is looking at how well a process uses the available resources. And so if we look at it, we can basically say that, well, if I have heat transferring to a system, it's either used to do something or it's just lost, okay? It's wasted. Think of that fire I talked about in the first video. So you do a fire, you're going to cook, it warms you a little bit, but most of that heat is just going out to the environment. It's wasted. So if I do something like this, I can think of this as a way to come up with quantifying this quantity. And so an exergetic efficiency or second law efficiency, they use the notation of an epsilon. It is the heat transfer portion of the exergy that was used divided by what there would be if it were a perfect world, ideally, what was coming in. And the reason that this is useful is that I can use this as a way to think about what I might do to improve my use of resources. So I can increase this number here. Okay? So one way I would do that is to make QU closer to QS by reducing the lost heat transfer. In other words, insulate my system so that any heat that I'm trying to use actually does get used. Another way I might improve this efficiency, improve my use of resources, is to modify TU. Okay? I would like this to be as close to TS as possible. Okay? The closer I can drive this to the temperature of my source, the better use of my energy I will have. Now, I'm not going to ever actually achieve either one of these things, but that is a goal as far as use of resources and working towards a goal of making a better world. Now, just one little practical point though, think about like a home water heater. Most people do insulate their home water heater, but nonetheless, you still only have an exergetic efficiency of roughly 10%. Most of that heat is just being lost to the surroundings. So there's a lot of room for improvement in our everyday life. And As an engineer, we can look at ways that we can make those improvements, and one of the first things is having the available tools so that we can actually quantify these. So that concludes my videos on Exergy.